row, but I'm told that Kathryn is very civilized when it comes to how she deals with the front row. So, and I'm sitting up here, so okay. So you're welcome to join us in the front if you need more seats. So let me just say, I'll be super short, but let me just first of all say welcome to everybody, and welcome to our first instance of the Goldman Sachs Distinguished Lectures in Computer Science. And you know, this is kind of possible because about a year and a half ago, I met Gene Levinson. He's at Goldman Sachs, and he'll introduce himself in a minute and tell you about Goldman. But and he and I really hit it off, and we enjoyed each other's company. And he said, you know, Goldman would like to get more involved with the University of Utah in computer science. What can we do? And we started brainstorming, and this was the first idea we came up with that we felt really worked. And so that's sort of the background of what's going on here. So welcome to everybody. I'll let Gene say a few words about Goldman's perspective on this, and then Mary's going to introduce Kathryn.
All right, thank you, Russ. Well, again, good morning, everyone, and welcome to first series. And what I'm going to do is, in the next 92.5 seconds, I'm going to tell you why Goldman Sachs is sponsoring this. Well, the major reason is because this is a fantastic school, and myself and a number of folks from Goldman Sachs have had a pleasure of meeting your faculty and your grad students, and it's just a fantastic program, and so we wanted to partner, we wanted to do more. Some of you may know that Goldman Sachs happens to be one of the those premier investment banks, and we are. We have about 34,000 people. What you may not be aware of is that we have over 9,000 people in technology, most of them in computer science. So some people may say we're a sales and trading house, some people say we're an investment bank. Having spent the last 25 years in technology, I'd like to believe that we're a technology company that pretend to be an investment bank. After all, we are the largest division. So anyways, I know I recognize some faces. Some of you have gone through our internship program. Look forward to seeing some of you in our newly established co-op program. And I know it's a long ride. We're in downtown. It's about, what, 2.5 miles down the hill. So feel free. There's a number of Goldman Sachs people here. If you have any questions afterwards, we'll be here to answer them. With that, Mary.
To introduce our first distinguished lecturer speaker, Kathryn McKinley. On the professional side, she's a principal researcher at Microsoft, and she also spent many years at the University of Texas as an endowed professor of computer science. Before that, she was a professor at UMass Amherst, and she has won numerous awards, mostly for her research, but also she's an ACM Fellow, an IEEE Fellow, and she won the ACM SIGPLAN Service Award. She's currently a member of the Computing Research Association Board and also the CRAW, which focuses on increasing the representation of women in computer science. And she's going to talk to us today about some programming language work in the presence of uncertainty. On the personal side, I've known Kathryn since we were undergrads at Rice University. So going multiple decades, I won't tell you how many. We met in a class. It was a software engineering class, the kind you sit in the lab the whole semester and get to know your classmates very, very well. We were in a bunch of undergrad classes together. But when we graduated, we both decided to stay at Rice and get our PhDs, and that's when we became friends. So Kathryn and I were office mates at Rice for many years, along with John Carter, who used to be faculty here. Originally, the three of us were in an interior office, kind of like the CS office here, where there were a bunch of interior offices together. The faculty quickly discovered that we were very loud. And so they decided to move us far, far away from them. So they moved us to a different floor next to the elevator, so that we wouldn't disturb them anymore. At some point, they thought we were having too much fun, and they decided to separate us. And so we rebelled, and we won, and they didn't separate us then. So after grad school, Kathryn and I have gone on, continued to be friends, and let's see, we have shared a lot of personal and professional milestones. Professionally, we helped each other during the interview process, getting our first jobs, getting grants, dealing with students, changing jobs, promotions, and personally, we've gone through having our first children and dealing with raising them, and our first karaoke at a conference, and various other things that we continue to provide support for each other. So with that, I'd like to introduce our lecturer, my friend, Kathryn.
And I'm sure Mary and I are going to have lots more fun stories, and that's like the nicest introduction I could ever have. Thank you, Mary. So I'm going to talk to you about programming with estimates. And I'm going to start with a little story. Who's that? Is he fast? Does he run fast? Yes. How fast does he run? The 100. Okay, so what miles per hour is that?
It's like high 20s.
Yes. Whoops. There we go. 24 miles per hour. Fastest man in the world. Who's that? No idea. That's James. He's our intern. And he runs 59 miles per hour. And how do I know? Because that cell phone app tells me that. And how can that happen? So if you write on your Windows phone, get location, sleep for 5 seconds, get another location, and then add them together and print out the number, sometimes it'll tell you 59. So why is that? And it's because when you read the GPS coordinates, they aren't facts, they're estimates. And the GPS is never accurate to more than 4 meters. So if you're walking slowly or you're stopped, the readings can be random. But because it requires several satellites to communicate with your phone to be even that accurate, you can get a lot of error. And a building can occlude one of the satellites, and so then you get even more error. All right? So GPS sensors, accelerometers, heart pressure, are all producing estimates. And all these programs are treating them like those estimates are facts. And in fact, we looked at hundreds of Android applications and Windows applications that use the GPS, and you get an error value when you get a GPS reading on the location. And what does that, guess, does anybody look at that error value? No. One application looked at that error value, Pizza Hut. And Pizza Hut's choice was, if that error value was high, it wouldn't tell you what the closest Pizza Hut was. It would just wait and try again and see if it got a more accurate reading. And I'm sure all of you have had experiences with your GPS telling you crazy values. But estimates don't only come from sensors. Every day in all the software we're using now, machine learning is becoming a more and more critical component. Machine learning is producing an estimate. All the programs that are working with the machine learning take that estimate and then treat it like a fact. And this causes the kinds of mistakes that we saw earlier. Also, in this generation of computers that we're building today, more and more we need to find performance from doing things like approximation, or because you'd like your cell phone to last till you go to bed or plug it in. So maybe you're willing to have a more degraded experience in terms of your web browsing if that means the phone can last longer. So there are all these trade-offs in the system design space that people haven't been able to express at all in existing programming language. And if they do, it's all very hacky because the type system lets you deal with discrete values. It doesn't tell you how to reason about things that have error and estimates in them. So today I'm going to talk about a programming language abstraction and a runtime system and give you some more motivation on why you need it and how to do it. All right. So first I'll talk about giving developers, and in this case I'm going to focus on application developers that consume estimated data sources rather than the developers who are producing those estimates, but I'm going to put a little more work on those expert programmers, and I'll show you how to do that. And then I'm going to show you, once you have an estimate from a sensor or machine learning or wherever you're getting the estimate, you need more information, that the estimate isn't good enough. And what we do all the time to make those estimates better is add domain knowledge. And so application programmers are going to need some controlled mechanisms for adding that domain knowledge. And then now we've made programs produce random results on occasion, because when you have estimates, there's noise and sometimes it doesn't make any sense. So I'm going to talk to you, depending on how my timing goes, I'm going to talk to you a little bit about proving what it means and what's useful to say about a probabilistic program that can help develop the average developer. All right, so let's go back to our GPS program that computes the speed, and we're going to turn it into an uncertainty program. And so in order to make it a familiar paradigm, the application itself is still going to operate on discrete types. They're just going to be called uncertain types. So we're going to encode in the type system that I changed my talk from last time, so I have an extra slide here. So this is, if we plot over time those circles, this is the error and this is why we get trash. All right? So that's what you get with the discrete program. Now we're going to transform it into an uncertainty program. But we're going to build on discrete types, and the programmer still gets to say coordinate point and reason about a single coordinate point in each program statement. And the reason that works is because we're going to use a sampling-based semantics for the uncertain type. So this program executes on a sample from the distribution of the estimate. All right? And so as far as the program is concerned, it's a discrete value. It's a coordinate. So I just get to reason about it in the same way I reasoned about it before. But now, when you get to your conditional statement now has a new meaning. And it is a hypothesis test. So instead of testing is speed greater than 4 as a discrete type, we're going to say, is it more likely than not speed is greater than 4? What does the evidence tell me? So the runtime has to implement the statistics instead of the developer. All right? But this is a hypothesis test. This is simple to implement in your runtime system. And just by writing this program, we get rid of most of the trash, okay? But we don't get rid of all of it, okay? Because when it's very uncertain, we say, not really, right? And we just are printing out the values that we have higher certainty about. And then we can, so that's 86% fewer errors. So what is this semantics on what we're doing? So now I'm going to walk you through what the runtime does in order to figure out if speed is greater than 4. So we're encapsulating probability distributions and hiding the statistical complexity from the programmer. And you get to compute over the random variables, and we have this special evaluation of conditionals. So even though the GPS is not Gaussian, I'm going to use Gaussian because building on your intuition, because everybody in here, I hope, has taken at least one statistics class and seen these examples a lot. So if we have two distributions, x plus y, then we can take a point out of these two distributions and add them together, and we get another Gaussian distribution. And that's, the statistics for that are correct. But what happens is, when you add those two together, the error gets bigger. And this is a key place where developers are making mistakes, because they're not reasoning about the fact that once you take that estimate and add it to another estimate or add domain knowledge, the errors are multiplying, all right? And this is a source, this is why the GPS speed is even worse than the error in the individual GPS readings, why we got 59. So, capturing this effect in the computation is a critical part of our runtime system in order to do this correct. So when the program executes this statement, d equals a divided by b, when they're uncertain values, the program doesn't actually execute it immediately. Instead, it builds a Bayesian representation, a plus b, and divides it. So the runtime, instead of doing data flow or doing the computation, builds up a little Bayesian DAG that represents the computation. And because it's the actual execution of the program, all the cycles get flattened, so this representation can be large if you're doing a lot of stuff. So, and you keep building this until you actually have a hypothesis on the data. So here, if you do some more computation, we build another graph. So for example, if this had used B instead of D, then we'd have to connect B directly to both things. So it is a DAG, it's not just a tree, because we want to use the same sample for the redundant computation because it's the same value. All right, so when we get to the conditional, that's when we evaluate the Bayesian network, all right? So you compute the probability that the speed is greater than 4, so you have to take samples from the distribution of the speed in order to make that determination. So you have the values of the computation in your Bayesian graph, and then at the conditional, depending on if the evidence is very strong or weak, that determines the number of samples that you need to take from your computation in order to do this correctly. So who's providing the samples? Too many animations. This is the key thing. And if you want more than 50% confidence, say you want 90% confidence, then you can use that as a parameter to your hypothesis test. All right, any questions so far? All right, so now we have this graph, and when we take a sample, we take a sample from the previous location and the location, and then we do the addition on it, and then we divide it by 5. If you have a constant, we coerce it to a point mass distribution and always return 5 for it. And so then you compute that. We can represent arbitrary sampling functions. So if everything is known distributions like Gaussian, producing the distribution over the sum, many of the distributions can be computed in closed forms, but it's actually easier to do the math in many cases and not encode it all in the runtime if you represent the distributions as arbitrary non-continuous functions, but it also gives you flexibility. For example, I'm going to show you a road application. You can't really describe roads with Gaussians, although you could a little bit. Gaussians are roads are much more easily described with arbitrary continuous, non-continuous functions. And the GPS distribution is actually a donut. So the dot you see on your screen is a location you're least likely to be, because you're most likely to be in this little red part around that dot, okay? But it's not a good, you can ask Chris, that's probably not a good representation that human beings would like, would be a donut with a little probability distribution around the zero, so around the inside, so that's why we have a dot, all right? All right, but someone has to write it. And so we rely, for example, on the GPS expert or the machine learning expert to tell us about the distribution. So in the case of GPS, we can use the built-in Raleigh distribution that's in a statistics package, or a Gaussian distribution that is provided by the runtime to give us a sampling function. Or we can use a random number generator to choose points probabilistically from these arbitrary non-continuous distributions. So, but those programmers know their error models and are expected to be experts in GPS or machine learning. And one of the ways we do this for machine learning is build multiple machine learning models for the same thing. So one of our applications is a neural net that does edge detection. And so in that application, what we did to build an error model for what kind of errors the neural net was giving us was build multiple neural nets by having different starting points and different numbers of interior nodes, and then we can sample from those multiple neural nets to get more accurate results. All right, so now we've talked about how we're doing the evaluation of the speed, and this naive one gave us these 30 false positives. This turning it into the hypothesis test gets rid of many of the false positives, and then if we want higher accuracy and fewer false positives, but also lower recall, so sometimes we're going to miss points that are true because we're requiring this higher statistical confidence in the answer. All right, so that's how we get a good result, and that's how we improve the accuracy of programs that use estimates. Now the next way we're going to improve the accuracy of programs that use estimates is we're going to exploit context. And so I'm going to again build on an application that everybody loves and appreciates, which is your GPS directions on your phone, which has completely changed my marriage, not arguing about how to get places, just trusting, listen to her. She's telling you which direction to go. I was an early adopter of GPS technology. So some of what I'm talking about with you today in terms of proving accuracy is now shipping in Microsoft's fitness band. It's called the Band, and it's getting great reviews. If you haven't tried one, go to a Microsoft store and try one. And also, but also we wrote the applications on a GPS phone, and many people are using GPS for restaurant. I should have put Pizza Hut up here. That was a mistake. Oh well, I can improve this stuff. And but when your GPS is in your car, you know something about the signal. You're most likely on a road because cars are most likely on roads. Not always. All right. And so right now, what programmers of the GPS software have to do is make very convoluted decisions about when to draw you on the road and when to say, well, maybe this is a parking lot that's not on the map, or maybe the road has a detour in it today and they built a new road. So how you program that right now is a nightmare, but you can do it. So here is a systematic way of what we'd like to do is, here's your GPS reading. here's your road as a arbitrary non-continuous distribution. We'd like to say, put those two things together and give me a location. All right, so in this Bayesian representation of the putting together the prior, which is the map, which says, using my domain knowledge that this GPS application is going to say you're most likely on roads, together with the likelihood, which is your GPS reading, because it's saying to some sense where you are, and you can produce a posterior distribution, and you have to be able to say the weighting of the prior evidence based on the likelihood function that you have. So what I've drawn here is making it 5 times more likely that you're on the road than you're where the GPS says. So that's why we have this huge spike here and this slow drop off. You could weight it much higher, right? That's a trade-off I'll show you in a second. All right, so how do you do that? So we're going to add 2 constructs to the programming abstractions I've told you so far. We're going to add an ability to build this probability distribution, which says 90-10, 80-20 as to whether you're on the road or not. And then we're going to let you, just like Bayes' rule, we're going to let you say GPS, hash map, and that just slams them together in composition. And so now in 2 lines, you can write what's taking thousands and thousands of lines in your GPS application. So here's the details of how we do a sampling function on maps. So what part of the map do you want to hash together with the GPS location? Well, what we chose to do is take your GPS reading, draw a circle around the bigger donut, and just like I said, is inaccurate, but that's what we're doing. We can draw it here. And all the roads that fall in that circumference, we're going to take the road segments, the road and the segments, and use those as the nearby roads. All right? And so this, I'm not showing all the programming you need to do, but it fits on the page. All right? From using Bing Maps or Google Maps to grab the roads from a GPS location is a call, so you can make that, or you could cache your usual maps on your phone to make it go faster. All right, and then given that sampling function of roads, all we really do is take the GPS likelihood function and put it together with that road prior, and we're done. So now in 2 pages of code, we've done what people have done in thousands of lines of code previously. And so those 2 lines of code with this 5% more likely give us a correction from the GPS road snapping that's not perfect, because if I really wanted it always to be on the road, I would need to add acceleration and a few more things to do a little better here. But I'm just showing you the power that we get with those 3 lines. Elaine, you had a question?
Yeah, maybe I missed it, but you were using you got the prior, but that seemed to be the issue with the map, but you don't have anything about where the last reading was. Did I miss that?
So I have a
GPS.
I'm not using speed or acceleration in this example. If we did, we could be a lot more accurate. All right? All I'm using is the GPS to find, and then I sample the actual roads nearby. And so if I use the projection, like 3 points in a row, you could definitely snap to road a little better. It would require a few more lines of program and more talking.
Okay.
So I'm trying to make the examples as simple as possible and show that there's a lot of power even in the simplest cases. All right. So now what the developer needs to do to tune this program is to come up with a weight on the prior, Like how much do you want to weigh the road? And in this case, James, our intern, was on a bus and was on the road the entire time. And so by weighting the prior 100%, we would be more and more accurate, all right? But not every problem's like that. And then then you also, the next parameter you need to tune for this program would be the search radius. If you make the search radius too big, you're including a lot of random roads that aren't really helping you. So there's a sweet spot. You don't want to make the circle too small, but you don't really want to make it too big. So 2 meters, sorry, don't know what the units are for this, and it's unlikely to be 2 meters. So I can't remember that, I'm sorry. All right. So that's another parameter you'd have to tune as the developer. All right. So in order to evaluate the expression I just showed you, you can't just do a hypothesis test anymore because you need to combine multiple probabilities together. But the DAG representation is still a valid representation. But now you need to go down. You go down several paths in the program execution. So we need a way to weigh the samples. So some samples are more important than others. So we use importance sampling. And in that case, you still write the sampling function that I showed you on the finding the nearby maps. But instead of each sample being weighed the same, it depends on which path you went down the program and the likelihood function that you're using. All right, and then which one you use affects how long it takes to evaluate these hypotheses. So the weight that you're giving to the prior, the more weight you give to the prior, the more you have to correct the GPS, okay? The more wrong the GPS is going to be, because the more you're going to say the road is correct and the GPS may or may not be on the road, all right? And then there's some non-continuous behavior where you actually have more accuracy at less time, and the reason for that is when you require more accuracy, it's sometimes quicker to evaluate these conditionals, right? And in that middle range, you don't know as well. So one of the key things here is, oh, it looks like you're adding lots of time to do sampling. Well, we are. But it's much cheaper to sample the errors than it is to do one GPS reading, which is very time-consuming and expensive, or do the machine learning algorithms. These tend to be more computationally intensive and this just takes like a few microseconds to do the sampling, right? Much less than it takes to do a GPS readings, which is in the hundreds or in the thousands. All right. So now, questions on that part? Yes?
So I have a question. Well, I guess partway it goes back to the first part, but maybe if you address it later, I can make that. When you're building these DAGs, in the first case it was a simple division, but things can get more complicated.
Yes.
Now, it is no longer obvious how many samples you need at the top end to get a particular level of accuracy at the root of the tree.
Right.
You have to have some way to know I've done enough sampling that I'm confident that my answer is going to be, I've got the distribution basically.
That's right.
And how does the system automatically or otherwise figure out how many samples a reasonable number to get?
So when you hit a conditional, you have a default number of samples, and we're looking for a 95% confidence interval. And so we take that many samples, we see if we make the confidence interval, and if we don't, we take more samples. And because we're actually relying on the medical literature for adding samples to a sample set, for these simple representations, the statistics for that are correct. So you don't have to choose say 1,000 samples, you could say 100, 100 more, 500 more, and then get to 1,000 and you can use all those samples. That's a good question. Because it's based on that conditional test, We have a default number of samples, and then we just add samples. So you can express, just like you don't want to divide by 0 in discrete programming, you do not want to compare two estimated values because we can never determine that. So you would add to your runtime an exception or some other error condition to represent things that people shouldn't be trying to evaluate. Or if you could also detect equality, you're trying to do equality in your if statement at compile time and not even let you compile that program.
So I have a quick question. So are floating point errors at all a problem here? Do they even matter? When you do sampling and things like that, I guess you're sampling in floating points. And then you have floating point error. I don't know if that creates sampling. I don't know enough about
If you have a floating point number and you're sampling floating point numbers, then you're getting a discrete floating point value every time it has some error in it. So you're just reasoning more explicitly about that error. You could encode floating point error in our model, although we haven't done that.
But are you sampling like to try to avoid like probabilities going to 0? Do you do things like putting logs in the sample?
Say that again?
Right, so if you're compounding a bunch of small probabilities,
Yes.
right, you do have floating point errors where you can, truncate down to 0 and have these vanishing probabilities. Common problems.
So,
deal with that in any way?
So we don't do anything special for that.
Okay.
But it depends on the hypothesis that you're trying to evaluate,
Sure.
right? And so you can express things that can cause the system not to terminate. So we in practical situations we didn't see that, but definitely you would, in a full-blown implementation, you'd want the runtime to say, okay, I give up, and I don't know is an appropriate answer. Sometimes you can't tell if X is greater than 5 or X is less than 5. Right? And so you want a tertiary condition that says, if neither of these were true, maybe I want to do something else. That's a good question.
In the example you mentioned, for example, the GPS examples, you kind of use the road information as a fact to justify your algorithm.
Pardon? What did I use as a fact?
For example, the road information.
That's right. Well, in this case, we knew that the prior is we believe you're on a road, and for the example that we used, we know that James was on the road the whole time in the bus.
But it is always the case that you have some facts reversed to justify your uncertainty.
So the domain knowledge is something about roads or human beings. So if you're doing machine learning for the connect, which is another example we did, and you're waving your arm, okay? There's only some certain speed that humans can go at, based on Usain Bolt, 24 miles an hour. So we could use those limits, the physics of humans or the physics of motion as ground truth. So it depends on the domain you're trying to solve as to what priors are reasonable for your domain. And so those are, they could be facts, but they could also be probability distributions. And so in the case of a road, we think you're on a road because this is in a car. Cars are usually on roads, but not always. And so you want to control the weight based on how strong your prior is. All right, good. So, in programming languages, we like to talk about facts. And we like our programmers to tell us stuff about their programs so we can help prove them correct or incorrect or give them guidance either statically or at runtime about whether their program is doing what they want it to do. So, for example, you want to assert this file is not equal to 0 before you start writing to it. As an example assertion, we'd like in programming languages that we'd like people to write. All right. So now we can test, verify, check these assertions and help you write better programs. And what does that assertion mean? It means that E must hold on every execution of a program. But now we have introduced a semantics where that's not true anymore. And we have the examples that I just showed you, where we can never say exactly how fast you're going. But we also have, in approximate computing, the image is close to the precise version. K-means clustering is likely to converge on unreliable hardware. So this assertion that holds on every execution isn't the right way to express that, all right? And another example I'm going to go into a little more detail is obfuscation for privacy. So if you're going to obfuscate your data, you still want to have data that's close enough to the original that you can use it. So how do you express that in any of these programming languages? Well, you can't express that with a traditional assertion. So we're going to add a probabilistic assertion, all right? So here's an example of obfuscation. So you have some true value, which is the average over all your public salaries, I guess, in the University of Utah and Texas was the same, but my salary is now private because I work for a company. So, but maybe Microsoft wants to compute the average salary of everyone and use it, all right? So, but they want to obscure people and make it private. So they have this obfuscation where they add random noise into the salary. And this is a way that we're trying to get actually people to share medical data with us. That we're going to use your data, but you're not going to be able to self-identify. And the theoretical community has done a good job of designing some algorithms that actually do that. But how about the implementations of those algorithms? How can we prove that they're doing what you want them to do? And you can't assert that the true average is always less than or equal to $10,000. But hopefully, we're going to let you prove that, prove it this way, and let you say something probabilistically about it. So we have a probabilistic assertion. We have an expression. We have with what probability you want it to hold and what confidence you want it to hold. And just like we did earlier in the talk, we had 50% as our default probability. If you leave off P, that's what you get. And our default confidence interval is 95%. So if you leave that off, that's what you get too. All right, but you can completely specify these if you want. And now what we're saying is expression E must hold with probability P. So now we can describe these programs that are doing things with estimate much more rigorously. And so now, how do we verify that? All right, so here's our probabilistic program, and we want to have a P assert about it that says that we're close to $10,000, and we need to verify it. So, naively verifying it, you can just run this program lots of times and see what it produces, okay? And then if you run it over representative distributions of your data and you run it enough times, you can develop some confidence, probabilistic confidence, that you have the correct answer, all right? So this is, by default, one way to get a semantics for these programs. But you have to be careful in that your inputs, in this case, we're adding Gaussian noise. We're saying that the amount of noise or the type of noise we're adding is Gaussian, but you need to do this for each kind of problem the same way I showed sampling functions for the Raleigh distribution and also for the maps. Okay? But can we do better than this? Let's see. All right, so what we designed in our PLDI 2014 paper is a distribution abstraction via symbolic execution. So very similarly to how we evaluated hypothesis at runtime, we build up a Bayesian DAG. And now the difference here is this has to be a symbolic execution because you can take different paths, the loops could be on a conditional, and so we have to represent more of the program, just like partial evaluation. All right? So we have a representation that looks a lot more like partial evaluation. But one of the things that happens by doing that is that these Bayesian networks that we have are now amenable to statistical optimizations. So for example, if you're computing the average, we can apply the central limit theorem. If you're shifting a Gaussian by a constant, we can do that inside the compiler. So we can simplify many interesting problems and optimize these Bayesian networks. And then by doing that, we can actually apply this back to the previous runtime support as well. But right now, we're just doing it in the proof system. All right, and that gives you a simpler DAG, which is easier to sample. And in some cases, we can verify it precisely, depending on if we have known distributions with closed forms. So there's some of the statistics in several cases let us evaluate it directly without doing sampling. All right, so here we did the GPS walking. So if tell your GPS, will you track my walk today? And so we know a limit on how fast you're going. For privacy, we did the salary, the application I just showed. And then for approximate computing, we did the k-means machine learning algorithm, the Sobol edge finder, hotspot detection, and inversion K2J. I don't remember what that is. So this was joint work with Adrian Sampson, who's going to be on the faculty at Cornell next year, and he's been his work has been in the approximate computing space, both on the PL side and on the architecture side. And so these were applications he was interested in. All right. So this shows the baseline for all these applications. If you just sample everywhere, you build up the graph and then you sample it a bunch of times, and you get a slow sampler. So by just building the Bayesian graph and sampling the Bayesian graph instead of sampling the entire program, so the partial evaluation does all the discrete computations, and it only builds a Bayesian graph for the parts of the program and reevaluates them during sampling. And so just doing that saves you a ton of time because you're not doing all the discrete computations. Because even in these programs, there's lots of discrete parts. And then if you add on the statistical optimizations, in these these two programs, we can directly evaluate it, so we can prove it for all inputs and all distributions. And so that was nice. So, and most of the time, the blue time is analysis time. So that means we spent our time simplifying the graph, and so you can also not optimize highly. So you could lower that time when it's in the blue if we did our optimizations faster. All right, so I've given you an overview. I've used a really simple example. We have some richer examples in any of the publications using machine learning, using the Xbox Connect, using the band to do gesture recognition. So if you're interested in digging into more of the details, I'd be happy to share the papers that have been accepted so far. We have the paper on the middle stuff for exploiting context that I showed. That paper has not, hopefully will be accepted to ASP+ in a couple weeks, but if not, somewhere else. So before I end, I want to talk about the IEEE floating point standard. So prior to 1985, we had floating point numbers, but none of the hardware vendors agreed on how to represent them. So if you needed to do floating point computation on different architectures, you had to modify your program. So in 1985, when I was just starting grad school, the IEEE floating point standard was made. All the architectures could write to it, all the software could assume it, and so this was wildly successful because it was the right abstraction for a set of programming numbers. Is it the perfect abstraction? No, but it's good enough, all right? And so that made all the software portable, that made the errors more deterministic, and so that was hugely correct job to do. We are at a similar place in computing history for estimates. All these applications, sensors, everything we're doing is now dealing with estimates. None of our programming languages have abstractions that make it a productivity way to program with it. All of our programming abstractions right now that people are using are just completely torturing the developers to deal principally with the statistics. And what I've shown you here today is one possible solution that is embedding most of the statistics in the compiler and requiring very little of programmers. There's a line of work for the people who are deeply understanding statistics and machine learning called probabilistic programming languages, which we're kind of a subset of. And their focus has been on the expert programmers, where you want to express the sampling algorithms and what kind of inference algorithms you use, and you need to be able to tune those much more directly. And so that's giving the statistics expert a set of tools. But what I've argued today is that the rest of us also need a set of tools to deal with this. And I want to thank you very much for your attention. Some more technical questions, and then I want to share a little personal for the grad students at the end.
So, you talked about the verification step.
Yes.
So, is there a way for the system to know that it cannot know? In other words, is there a way for the system to say, if when I had known Gaussian distribution, I could infer something about all that dispersion, but you give me description that I don't want to handle, I cannot give you this. Is there a way for it to know that it can't know?
When we have an input, right, and we're just sampling the bunches of different inputs, we haven't described them as a distribution. That's a case where like we don't know what we know, all right? But in all these cases, we were able to describe a distribution over the inputs, or know that we had Gaussian. So when we have distributions that are non-discrete, we can still do some verification. So we moved it much further, but of course we haven't solved an unsolvable problem, which is if you don't know anything about the inputs, we can't tell you anything about the output of the program, right?
Yeah, really insightful talk. So I wanted to ask questions. You have worked for so many years in computer architecture, parallel computing, and now you're into this area. So
how did I get here?
Yes, no, well, so that's also one question. But suppose you go back to your computer architecture role, what would you do in computer architectures to exploit this approximation? And would that serve all communities? I mean, machine learning may be able to get away with software results, but not HPC maybe?
So why I'm working on this problem is because I wanted to work on data center efficiency and phone efficiency and do energy optimizations. And when we looked at all these cell phone applications, there was no way to express the trade-off between energy efficiency and quality. All right, there was no way for me to say as a programmer, hey, I'm willing to degrade my output because I'd really much rather have my phone work until I go to bed. All right, and so this quality efficiency trade-off wasn't at all expressible. And then what was the root cause of that? Well, the fact that we were doing all this estimated computing seemed to be like the deeper, more important issue. And so we need to, so I'm still hoping to improve energy efficiency through this programming model, but in order to like solve the deeper underlying problem, we had to take a step back. And I think that what this says for computer architecture is the application layer has to be expressing things that the computer architecture can now optimize, which is energy efficiency. But in order to do that, you have to say what you're going to trade off, because there's no free lunch.
Do you have a strategy for dealing with distributions when samples are not independent, that is, there's non-zero correlation between successive samples?
So if in programming languages, if you have data flow, you can actually determine what distributions are dependent on each other. So there's some dependence testing that we get because we're in the compiler, all right? But if you have two inputs that are correlated, that we're reading in from the application, we require you to overload the operators that say what the conditional probabilities are based on these two inputs. So we assume inputs are independent, but we let you specify to override.
Did you override it in the GPS example?
No, because the error in the individual readings is actually independent.
I actually think it's not. I think GPS samples taken close together in time and space are actually very highly correlated. That's why differential GPS works so well.
Yeah, but it's the error that's independent. And the error, like you can be in the same place and a satellite can go out of scope.
Sure.
And so yes, it can be, there can be some dependence, but it's independent enough, right?
I'm not so sure. Do you mind going back to slide 16, please? Because here, for instance, the sort of pink background is a 95% confidence interval, right?
No, the pink background is correct, is the 95%, yes, the pink background is 95% confidence interval.
I suspect that this confidence interval is actually much too wide, because in a true 95% confidence interval, that would mean that in the limit, 1 out of 20 such intervals should fail to include the true value, whereas if we assume ground truth is in the range 0 to 5 miles per hour, actually all of your intervals include it. So I think that's more like a 99.9%.
Well, because you're walking slowly. The GPS error is 4 meters. You can never be more accurate than 4 meters from GPS.
Well, I think that comes back to the correlation, because you're subtracting successive samples where I believe the error is correlated. I think the actual variance in the difference of positions is going to be lower than the variance we're estimating. So I believe those intervals should be much narrower, to the point where really 1 out of 20 of them should.
So you're correct in that the GPS experts can, and they do, compute a more accurate speed than I've computed by doing the differential and reasoning about the correlation between the two readings. All right, but you can take each GPS reading, and it is an independent sample, because you've moved, the satellites have moved, and you're taking them over a long enough period of time.
Well, okay, I agree over a sufficiently large interval of time. I'm not convinced.
You're not taking you cannot take a GPS reading really quickly, or your phone dies anyway, right? But there's better statistics you can do if you don't expose if you're doing it inside with the correlation analysis.
Right.
I have
multiple data sets that we're using to evaluate, come up with some type of an estimation. Will we be able to control the weights of the inputs, or would there be some transparency into those on the outcome or the result?
So yes. So the conditional probability, you can express that and you can make it a function, an input to your program too. So if you want, on some executions, you want to weight it more or less, and you want to make that dependent on the actual data set, that's easy to encode.
I'm curious if there are examples where you want to actually expose to the programmer the full distribution and map sets.
Samples?
Yeah.
So the developers can, if you want to describe your distribution and work with it in different ways, you can. We're not precluding that. Because it's the data set that, like for her question, the data set you're using has some expert that's describing stuff on it. And so if you're that expert, you can do more stuff with the distribution.
Yeah, so I guess following on that, then you mentioned the probabilistic programming language.
Right.
And so if, do you subsume any of that? Like, how much influence do I have on
We don't subsume that. We're a subset of it. We've restricted the programming models so that we can do automatic inference, so that the developer doesn't have to choose the inference algorithm or the number of samples. And sometimes the conditionals that you say, we can't evaluate, right? So we just stop sampling at that point.
But so your expert functions here, or the functions the experts are writing, are they being written in the kind of probabilistic generative casting language?
No, but one of the proof of concepts we did was take uncertainty program and produce a .NET program, where then you could choose the inference algorithm, for example. Because we are a subset, you could expand to the richer semantics.
This is very cool.
Thank you.
I have a question about the way you generate the Bayes-net. So let's say in the example that you had something like A equals B plus C, so
right.
you create this little Bayes. How do you handle the case when B equals B plus C? So you can't avoid having a loop, and that kills the semantics.
So we use static single assignment in compilers. We just give them a new name.
Oh, okay. And
because we're compiling.
I'll follow up on that later.
Okay.
So a question about probabilistic assertion. So the exception procedure of probabilistic assertion is symbolic execution procedure. So is that the only way to verify probabilistic assertion?
I don't know the answer to that. I'm sure there are other ways to do it.
Another question. So uncertainty is based on some buffers on the So what if there's some countermeasures? Suppose I want to express the property that 8% of the different area is greater than something, so I can probably use contrast, like for all the areas, the value is greater than something, and the probability is.
So we don't infer, we make you express, let's see. We make you express the probability distributions explicitly, and that limits the amount of inference we have to do. If you express those in your program and want an algorithm to infer the distributions from what you've expressed in your program, you're producing a model that's much more general, and the probabilistic programming people could handle that. But that is, we've said we don't want to do that because then we can't automate the inference algorithm. That's the choice we've made. All right, so since everyone's starting to leave, that's the last technical question. But I always like to say to the graduate students something more about me. Let's see if I can get learn more about me stuff. And so I'm here, so everything must have gone great because I'm so successful. Right? And so it hasn't always gone great. But lots of things have gone wonderful. So I've had 3 mentors in my life. Don Johnson, who's still in the emeritus at Rice, Ken Kennedy, and Dave Stemple, my first department chair at the University of Massachusetts. And I wouldn't be doing research at all if it weren't for Don Johnson. I took a course from him. He was a great professor. I liked him. I wasn't the best student in his class. I came up to him and I said, I would like to stay in Houston for the summer because I want to stay with my boyfriend. I didn't say that part. and do you have any openings? And he said yes. And so I worked on the first discrete event simulator that he and Bob Jump had built. And I proved that the bottleneck in a local area network was not the network, it was the disk. And everybody was really interested in that result, and they looked at my code and they said that it was correct, and they were surprised. And I realized this is totally not like doing homework problems. And so it made a huge difference in my career. And then everyone has a wonderful advisor story, so I won't tell you mine. And then that summer, I broke up with that other boyfriend, and I got together with my husband, who I've been married to for 30 years, and we have 3 kids. And I'm fortunate to have a great husband. But it hasn't, even though I've had a lot of success, and I got to testify in Congress, but on Valentine's Day, there's always like some horrible part to it. And I failed a lot. And so part of failing was when I graduated as an undergrad, even if I wanted to get a job, I didn't get any job offers. So I went to grad school. But I wanted to do that more anyway. But that was confronting. And then when Mary and I were office mates, she and John passed their qualifying exams, and I failed mine. And so in order to stay in graduate school, I was like, well, maybe this isn't for me. And I was very discouraged. I was going to drop out. But you couldn't actually drop out until later because the tests were in the middle of the semester. And so I went to Dr. Golson, who didn't get tenure, and I said, hey, I'm going to drop out because I failed. And he said to me, oh, but we think you can pass. And I'm like, really? And so I got rid of the television. Yeah, I put it in the attic, but that wasn't far enough, so I took it to my in-laws' house. And one of the other graduate students was away, and I moved into his office, and I studied every exam at Stanford, Illinois, and Rice. And when the NP hard problem was on the test, it was one of the ones I'd studied, so I just wrote down the answer. And this preparation in the face of failure, having all the right information at your hands, was a lesson I have applied in many cases. And if you want to be in control of the meeting, be more prepared than everybody else who's at the meeting and have an agenda, and then you'd be amazed what you get, the number of things you get to do your own way. And then when I was an assistant professor, I had my first year where you expect it's going to be hard. Well, in my second year, I had a son and I never slept. And I didn't have a single grant proposal within my first 2 years, and that was a very tough time. But then I took my grant proposals that were getting rejected, I sent them to some other people outside my department but in my field, and they gave me feedback, and then, yes, I got some funding, yay. And then, but that whole learning experience as assistant professor was very tough. What was for many years my most cited paper was rejected 3 times. And what did I do to get that paper accepted as the strategy I now use in many papers? I took the related work from the back of the paper and I put it in the second section, and I did a much better job of saying, this is what's wrong with everybody else and this is the problem we solve. And then the paper got into ASPLOS and I got tenure. And really, that paper was very pivotal in my career. And I still get papers rejected, as we can see from my paper I talked about today that has not yet been accepted. So, but my idea is that when these bad things happen, you get to be depressed, whatever you need to do, drink beer, my thing is chocolate, do that for a day or two, and then try to take what you can from those experiences and try to do better. And so that's my advice for having a great career. Thank you.